double integrals over rectangles. All right. So before any further, a quick review of what we did in single variable calculus. All right. So here is my function f of x, right? And how we define integration is using Riemann sums, right? So what we did way back in the day is we created rectangles everywhere to cover this entire curve. And sometimes it was an over approximation and sometimes it was an under approximation, depending if we did the right or left Riemann sum. But the same process would work, right? And then we found out later on that the best way to do this is to use the midpoint Riemann sum. That gives you the best estimation possible, right? So these were each individual xi points and values, where each individual rectangle had a length of delta x, right? The change of x. And then we found out if we take the limit of all of these individual rectangles, right? We add them all up and it goes to infinity of this sum. That's what we define to be our integral. Or end up being one of the fundamental theorems of calculus, right? This is in the being our integration. That's how we integrate underneath the curve. Now the problem is, how is this done in 3 dimensions? And the process is almost identically the same, which is kind of nice. However, because it's 3 dimensions, we don't have just a rectangle. We kind of have a cube. Well, not really cube. Let's call it a 3-dimensional rectangle. That's probably easier to say. So let's suppose we have the surface. Okay, so this is surface with respect to x and y. Okay. Now, what we're about to do is, if we mimic the same thing and use rectangles, now I'm going to cut a little rectangle on the surface. Just like we did a rectangle, right? You just cut a little rectangle going down. And if I transpose it down, this makes a rectangle down here, right? And if I transpose this entire surface, just flatten it, now becomes, oh, all I'm doing is finding the area of this transpose and each individual rectangle in between. And that brings it up to the surface above. Okay, so that's exactly what we're about to do. Is instead of using, we're going to use this process here to do it in 3 dimensions. So given a simple rectangle on the surface and then transposing the entire thing down, and then just adding all of the individual rectangles or the individual heights going up, that's how we're going to find the actual double integration, or the actual area underneath the surface itself. Okay. Now the key thing when it comes to all this, right? What's the area of a rectangle? Is length times width. Okay. And in this case, our delta x and our height, right, with respect to f of that point, would be our length and width. Okay. Now in this case, it's going to be our change of a, not change of a, change of a. Why do I keep doing that? Change of our area times the height is going to be our indication of our rectangle, or a cube rectangle. Okay. Or another way to write this is the delta area, the change of the area with respect to the function, just like it would be over here. And now if we add every single cube up all together as n goes to infinity, right, if we take the limit, that's how we define our double integration. And the reason why it's a double integration, if you notice, it's a double Riemann sum. Because now we're finding the area of here and also the lengths of each one itself. If the limit exists, right? However, it always exists in our case. So therefore, we find our double integration, which will always give us the volume of the solid or surface bounded between 2 points. Okay. Now, before we do crazy stuff and do double integration, how we set it up, let's just do a simple little example so you can see how this would work out, okay, using Riemann sums. So let's suppose our region that we're doing it is a 2 by 2 region. So this is the region we're gonna be doing our cubes, rectangles there from, okay? And we're gonna find the volume of the solid that lies above the square and below our surface. So it lives above this curving, how we want it to. We're gonna find that volume that makes it between it, right? So in other words, like this. So what is this volume it makes with that, with this square? So we're going to divide into 4 equal squares, which we have here. And we're going to do both corners to find the volume. In other words, the left and right Riemann sum. Okay. So let's first do the left. Okay. Now what that means is each square, I'm only going to do the left, just like it was in single variable. So for the left one, it's going to be this one for this rectangle, this one for this rectangle here, and this rectangle there. So, and according to our equation, it's going to be the change of A times the length of each one. So therefore, if I go back down here, this volume is going to equal to, well, when I plug in F of this point, which is going to be 0, 1, times length was just 0 here, is just going to be 1, plus the rest of them, right? Because it's this Riemann sum. So then with this one, now I go on to this one, where this is the point 1, 1 times 1, plus the next one is here, so it's be 1, 2 times 1, and then lastly, the last one, which is 0, 2 times 1. And therefore, the right Riemann sum volume will now just be using the right ones. So for example, this rectangle, we'll be now using this one. For this rectangle, this one, this rectangle, that one, and this rectangle, that one. So for the first one, it would be the point 1, 1. Next one will be 2, 1. Next one will be 2, 2. And then finally, 1, 2. And that's how we get our over-under approximations, which, you know, the left Riemann sum is the under approximation, and the right Riemann sum would be our over approximation itself. So therefore, what would be a better approximation? Would be the midpoints. And then at this point, you would just plug in each point and just add them up because it's just times 1 to get the left and right Riemann sum. Now, what's cool about this is if this is my volume here, right? This is my surface here. We only did 4 and we were at an estimated. But if we grow even farther, what if we do instead of 4 equal squares or rectangles in this case, we grow up to much more. We triple it, quadruple it, you know, and you just scale it, go up and up and up. So therefore, we get a better approximation of the actual area, right? Because this is our over under estimation. And as we get larger in our portions, we get arbitrarily close to the actual volume it would actually make. So it's a pretty cool little illustration of what's actually happening as when n grows infinitely larger itself. But just like it was in single variable calculus, the best approximation would always be the midpoint approximation, where each point is in the midpoint of each individual cube rectangle. So this is our midpoint integration of double integrations, where each point here is the midpoint of the exact middle of a rectangle. Okay. So let's just do one example of it and just call it there, because we don't finding midpoints is pretty painful to do so. So let's try this example. So we want to use a midpoint rule with mn equaling 2, okay, to find the values of the integral from x minus 3y squared dy or dA, sorry, where our portion is very interesting, is from 0 to 2 and y is from 1 to 2. That's interesting. All right, so let's see what's happening. Okay, so our rectangular region is from 0 to 2 from the x scale, and from y it's 1 to 2. So it looks something like this. And since mn equals 2, therefore we're gonna have a 2 by 2. So we're gonna have 4 squares, just like we did last time. Okay. All right. Now, since we want to find the midpoint Riemann-Son, we have to find the exact middles of each individual case. So in other words, the exact middle of every rectangle, and then add them all up. Okay. All right, so let's see. I just start with the first one. What is this point? This is the point 1/2, because it's the middle between 0 and 1. And since we have 4 of them, this is technically 1.5, right? There, or 3/2. So what's the middle between 1 and 1.5? That's roughly 5/4. Or not roughly, but exactly. Now here it is. The length is not 1 anymore, it's actually 1/2, right? From here to here. And now we do that for all the way down. So we got this one. Next, we'll do this one. So the middle between 1 and 2 is 3/2. Going up is the same here. Again, times 1/2, and we keep going. All right, so we did this one. So this one up here is going to have the same x value, but now a different y value. This should be 7/4. And then the last one back over here. So it'll be f of 1/2 up to 7/4. Okay. So this volume, again, after you plug in every single these points into our equation, and then just multiply by 1/2 gives that horribleness. I got something roughly looking like this. Now, question is, does this make any sense? No, right? Because it should be negatives. We're just gonna make it positive. Oh, why is it 1/2? Because the distance between here to the actual point we're looking for is just half. Because this delta area is just half of it. Yeah. Okay. Now forget about midpoints because that's like, everybody's favorite. Do one example, call it a day. Now let's actually do, how do we do integrations? That's the best part, right? So suppose we have the region A to B and C to D. And when we want to find and we have C to D of this integral, basically, what does this represent? So before we actually calculate the double integration, I want to give you guys an explanation of what is going on, okay? Or what does it actually mean to be a double integral, okay? So we have this rectangle, and usually it's in terms of x and y. X always comes first and y always comes second, okay? And we have this integral from C to D of our function xy dy, okay? So what this saying is this means the variable x is fixed only by integration with respect to y. Okay. So for example, if this area is equal to this integral, okay. All right. So now if we take the integral of both sides, so right, this is only in respect to dy. So we'll just take the integral of just y. X is considered a fixed value like a number, okay, just like it was like partial derivatives. So now if we take the integral of both sides, kind of looking like that. So now what this is saying is, I'm first going to take the integral with respect to y only first, evaluate that, and then I'm going to take the integral with respect to x, and then evaluate that. So it's kind of like a composition of functions. The innermost you do first, and then the outer you do last when it comes to double integration. Okay, that's a key thing. So now, most of the time when it comes to notation in our class, it's going to look like this. Okay, so what this double integration is respect to the region R, and that's what that region represents of the double integral. And this is going to be the delta A, because when you multiply these two, you get the area underneath the curve. Okay, so it's just simply quick notation purposes. And then you'll see how, we could actually change the bounds of integration as well. So instead of doing y always first, we could do x always first, and vice versa, right? Just like if we change bound integration in single variable calculus, we do the exact same thing here as well. Okay. But before we go into too much complicated stuff, like always, let's just do a couple examples so you can see how double integration would go by. Okay. So we'll just do simple ones, nice and easy ones, just get you comfortable with them. So let's evaluate each integral. So what the saying is, right, we're taking y first and then x. Okay, so I always, when I teach this and whenever I was learning this in college as well, I always do this to show myself I'm only looking at that first. So only those bounds. Everything else is second. So we're going to take the integral with respect to y. So this one right here. Everything else is fixed, right? It's just a single number. So meaning if I take the integral, this is just being 2x to the third, right? That's a fixed number. So integral of y is going to be y squared over 2. Okay. Now I evaluate it at 1 to 3. Okay. All right. So now this becomes, so 2's cancel, which is nice. So I just getting that. So remember, the key thing is I evaluate with respect to y. So y is the only thing I'm plugging in the values in. So if I plug in 3 into here, that gives me 9x to the third, minus plug in 1, that just gives me x to the third. Yep. So this just gives me 8x to the third. Okay, now that I evaluate with respect to y, then I go back over here and do the outermost. So now integrate from 0 to 2 of 8x to the third dx. And now I'll just repeat one more time now with respect to x. So this is going to be x to the fourth times 2. Evaluate at 0 and 2. And that's how we get our final answer. So plug in 2. 2 to the fourth, I think, gives you 16, times 2 gives you 32. The far so good there? Nothing too crazy yet, right? Yeah. Okay, so let's do one more, but now I change the balance to see, so you can see how the difference would be. Okay, so same thing. I'm just going to break this down. Okay. So now I'm first going to integrate now with respect to x. So this is what's being changed there. So if I integrate with respect to x, the 2y is going to be constant, so it'll be 2y on the outside. And now integral will be x to the fourth over 4. And that's be from 0 to 2. So this is simplifying to 1/2, right? And again, I'm plugging in for x only. So these cancel. So 2 to the fourth is, I think, what did I say, 16? So 16 divided by 2 gives you 8. So 8y minus plug in 0, just go to 0. Okay, so now I do the outer. Integral from 1 to 3 of 8y dy. And this is just follow the same template we did earlier. Plug in 3, that gives you 9, so it's 36. Plug in 1 gives you 4, 32. There we go. Now, notice it's the same question. I just changed the bounds of integration. And we actually got the same answer, which is very interesting. Now, this only occurs if we have one very special property. If we just have a rectangle, that's the only property that will work. So if f is a continuous on the rectangle, where r is bounded between a and b and c and d for x and y respectively, therefore, you could integrate with respect to the y and then x, or x and then y, and you'll get the same result in either case. Again, as long as f is bounded on the region and the integral exists. So sometimes it's actually easier to integrate with respect to one variable than the other variable first. That's why, you could change the bounds of integration, make it easier. Okay, so to finish up today, why don't we just quickly do this last example. All right, so we want to find the integral from this region here. So we get to choose how we want to integrate. The bounds are the same no matter what we do. It's still 0 to 1. So this is x and this is y. So why don't we just do the same thing as before? So we'll do this is gonna be 1. So let's do y first. And then x. It really doesn't matter. Okay. Now again, so integral respect to y, remember, so this is a constant like a 5. So that's just going to be x, y, minus integral of this will be y to the third, right? And that works because if I take the derivative, that's 3. So check how that works. And when I evaluate this from 1 to 2, again, only plug it in for y. So if I plug in 2, that gives me 2x. Plug in 2, that gives me -8. Then if I plug in 1, that just gives me x. And I plug in 1, that gives me 1. All right, so subtracting 2x minus x is just x. And then -8, this becomes a positive, gives me -7. All right, so now we're going to take the integral from 0 to 2, because that's the y component, I mean the x component of x minus 7 dx. Okay, so integrate this normally. X squared over 2 minus 7x evaluated from 0 to 2. So plug in 2, that gives me 4. 4 divided by 2 is just 2. 7 times 2 is 14. And then so plug in 0, just gives you 0, so this gives you -12. Right, last one. All right, trig one. So if we do the same thing, let's go, this is x to y. So this is going to be from 1 to 2, and then from 0 to pi of this. Okay. All right, how do we do the integral of y sine xy? Well, we can if you really want. This is actually integration by parts. And I'm pretty sure you don't want to do integration by parts, unless you really like integration by parts. So instead of doing it this way, why don't we use Fibuni's theorem and just swap integration portions? So now why don't we just do respect to x first? Like that. So now if we do respect to x, y is constant, remember. This is like a 5y or 5x in here. So we still have to use substitution. So let u equal xy. So therefore the derivative of this would just be y dx, right? So we would have to divide everything by y. So du over y would just be dx. So if we plug x back into here, this would be the integral from 1 to 2. The y's cancel, which is nice because I have to multiply it. Of just sine of u du. And I don't like changing bounds, so I'll just keep the same bounds itself. So now we just take the integral of sine, which is negative cosine. So this ends up being negative cosine of x, y, evaluated at 1 and 2. So this ends up being negative cosine of, remember we did respect to x, will be 2y, and then plus cosine of y. Yep. So now running that space here. So if I take the integral of now y at the end, so of all of this, dy, and I'm gonna have to do the same thing over here, but just for the sake of time, I'm sure you guys agree I could just, it will give you this out. All right, instead of just dividing by y, you divide by 2, and you get the same results. And the integral of cosine gives you a sine. Integral of cosine gives you positive sine, so these become positive. And you just evaluate at pi and 0, which is nice because it doesn't matter what you plug in. Sine of pi is 0, sine of 2 pi is 0, sine of 0 is 0. This whole thing ends up being 0, which is interesting. 0. They cancel each other out because it goes oscillates, right?